In this problem, a sign is hung from two cables as shown. We are to assume the setup is symmetrical and the sign has a mass of 20 kilograms. We would like to find out what tension must the cables be able to apply in this situation. First, let's start by drawing a free body diagram. We have a force due to gravity acting on the sign. We have a tension due to the cable on the right, which I'll call T1. And we have a tension due to the cable on the left, which I'll call T2. Now, because it says this is symmetrical, we can assume that there is a 60-degree angle between the vertical on each side, which means that there's a 30-degree angle between the horizontal and each cable on each side as well. We'll also start by just finding the weight of the sign. So it's going to be m times g. So the sign has a mass of 20 kilograms. We can assume we're on Earth with a gravitational constant of 10 newtons per kilogram. So the sign has a weight of 200 newtons. Now, in problems like this, we want to start by picking a coordinate system. I'm going to call up positive and to the right positive. And if you notice, our gravity force is okay, but our T1 and T2 are not in the positive X or positive Y direction, so we need to break them into components. So let's do that. We have T1X and T1Y, and we also have T2X and T2Y. Now we can use our rules of trigonometry to figure out how big these components are, and say that T1X is going to be tension 1 times, since it's opposite our angle, times the sine of 30 degrees, which equals 0.5 times T1. That's actually T1Y. And T1X is going to be T1 times the cosine of 30 degrees, which is 0.87 times T1. That's just using our laws of trigonometry. We can do the same for T2. If you notice, it's the same type of triangle, so we're going to have the same angles here. So T1 or T2Y is going to also be T2 sine of 30, which will give you 0.5 times T2. And T2X is going to be T2 times the cosine of 30 degrees, which gives us 0.87 times T2. Now we have everything broken into components. We can write some free body diagram, or use our free body diagram to create some Newton's second law equations. So sum of the forces in the x direction gives us T1x and T2x. So T1x is in the positive x direction, T2x is in the negative x direction. And since this problem is in equilibrium, we know these should be balanced out to be 0. If we then plug in what we know for T1x and T2x, we get 0.87 T1 minus 0.87 T2 equals 0. And if we solve this, this just tells us something very nice in this problem, that T1 equals T2. And this may seem trivial, but it's important here because it allows us to get rid of a variable. If T1 equals T2, we could actually just call them both T. And this tells us we don't really need any of our 1 and 2 subscripts here, that both tensions are identical in size. So we don't need 1 and 2 subscripts. So when we go to the y direction, you'll see how this is useful. In the y direction, we have T2y plus T1y, but we can call them both just Ty's because the x equation told us that T1 and T2 are the same. So I can say that Ty plus Ty for these two minus the weight of the sign is going to be equal to 0 because it's in equilibrium. Now I can plug in my numbers. Let's see, T2, the Ty's are both 0.5 T minus the weight, which is 200 newtons, equals 0. This tells us that T must be equal to 200 newtons, and we are done. And so again, to summarize what we did here, we drew a free body diagram, we broke things into components, we used the x equation to tell us that T1 and T2 are equal, and then we used the y equation to figure out how big the tension was. And the X equation result is also very useful because now in the future, whenever we see a problem where we have something hanging like this and the system is symmetrical, we can always assume now that the tensions in the cables are equal, and it saved us a step. Because this X equation is always going to come out to be exactly the same, where if these angles are equal in a situation like this, the tensions will also be equal to each other.